Let's talk about geometric series. So I want to remind you, we're picking up where we left off in class last time. So this is still part of 8.2 infinite series in the book. It's just kind of its own little subsection in there. So in class, we had this definition right at the end where we said a series is a geometric series if it has this format. So your index k starts at 0 and goes forever. A is some number and R is some number. So one of them is just a multiple on the outside, and then the other number is actually being raised to an exponent like this. All right, so below I have a few examples of a geometric series. And that third one you can see is in a really different format, but still counts as a geometric series. So in this first example here, it kind of perfectly matches the format that we've described above. So k goes from 0 to infinity, 2 is the a, and then 1/3 is the r. Alright, so we're actually going to leave some space underneath these because we'll come back and use some formulas on them. But for now, I just kind of want you to notice that it fits that format. So this particular series is a geometric series. So when you plug in values of k here, it's the exponent only on the 1/3. So you have 1/3 raised to the 0, to the 1, to the 2, etc. And then whatever you get as that output, you just multiply it by 2. So the 2 doesn't get an exponent. Okay, this second example here is also a geometric series. It's a little bit weirder, but it still counts. Here, it's -7/6 being raised to the k power. So my a is actually just 1, like there is no multiple stated outside of the exponent part. So I'll just say the a is 1, and then the r is this whole piece here, this -7/6, because that's the number being raised to these exponents. Alright, so this third example is extra weird for a couple of different reasons. And the first reason is that it's not written in sigma notation. It's written out just as the terms. But if the terms, were arranged in a nicer way, this would be a little bit more obvious. So what I want to do here is label the a and r the way that I did for these previous examples, but it's not immediately obvious. So here's what you want to do in this case whenever it's given to you kind of spelled out this way. Almost always it doesn't start with 1. So here's the thing. If it started out with 1, let's say we had 1 plus a half plus a fourth. Let's say it was really, really nice numbers like this. Then we would say, okay, I can see that this is powers of a half, right? A half to the 0, to the 1, to the 2, to the 3. So I can see my a would be 1, and then my r value would be this number here, which is 1/2. So that's what we kind of want to pull out of here. It's just that this one doesn't have a equals 1, this has a equals something else. So what we want to do every time is factor out the first number. So in this case, the first number, the first term is this 4. I'm going to factor 4 out of everything. And the reason that that is helpful should become apparent after we do it. So I have 4 and then a big set of parentheses. And now it's just every term that I see here, but now divided by 4. So 4 divided by 4 is 1. 2 divided by 4 would be 1/2. 1 divided by 4 would be a fourth. And you can start to see this pattern kind of come out again, where you're seeing powers of a half here. Okay, so the advantage to doing this is that now we can see we have a multiple, and now we have ascending powers of a half. So I'm going to say that this is 4 times a half to the 0 plus a half to the 1, and so on. So this is the a, this number that I have pulled out. And then my r is always the number that comes after the 1, right? Because anything to the 0 is 1. So then the next term you see has to be just the plain r value. So my r would be 1/2. Alright, so that took a little bit more work than the other two examples. But this method that we just did should work every single time. So when you're given the terms listed out like this, factor out whatever that first number is. And you should have 1 plus some stuff after that. The number you factored out is your a, And then 1 plus that second number that you see in those parentheses, that will always be your R value. If you want, you can put this into sigma notation, but there's no need to once you have A and R labeled. Okay, so like I said, we're going to come back to these examples. So I'm going to leave a little bit of space so that we can keep using that work for something else. So we'll kind of continue down here. Okay, so we are studying geometric series. Well, maybe I didn't leave myself enough space. Well, whatever, we'll figure it out. So we are studying geometric series because they happen to be a really well-behaved family of series where with like a little bit of creativity we can come up with formulas for a random partial sum and the entire sum of the series. All right, so the nth partial sum, we usually call it S sub n for any series, and that's the sum of the first n terms. Now, I do want to specify here, we're not going to spend a lot of time doing partial sums for geometric series, but I do want to make sure it's clear. So this would be the sum of the first n terms. So if we start at 0, that means that the last thing added is the n minus 1 term, because the 0 counts as one of them. So we would have a times r to the k, whatever that is for that geometric series. And we have a formula for what it would be. It comes out to 1 minus r to the n plus 1 over 1 minus r. Okay, so where this formula comes from is something that is really interesting, but because we're not, I mean, it's just kind of fun algebra stuff, but since we're not spending a lot of time working with this particular formula, I'm not going to spend time in the video talking about where it came from. You know what? I forgot the A. There should be an A right here. A times all that stuff. Sorry about that. Okay. So R in these two spots here is the R from your geometric series, and then the A that I forgot should just be a multiple on the outside. And then N is whatever partial sum you're doing. So if you're doing the 10th partial sum, this is 10 plus 1 up here. Okay, so we're not actually going to plug stuff in here. What I want you to notice is what we can decide about converge or diverge using this formula, right? Because one of the things we know is that if the sequence of these partial sums as n gets really big, if that sequence is convergent, then my series is convergent, and then we can actually compute that number. So the series would be equal to the limit of those partial sums. So as n gets really, really big, the only place n is in this formula is right here. So we're thinking about this formula, and then we're thinking about as n goes to infinity, do we have some sort of pattern here? And in fact, it depends on what r is. So if r is a fraction, and it can be positive or negative, but as long as it's a fraction less than 1, then this part right here, higher and higher powers of a fraction, that goes to 0. Then the sequence of partial sums, and thereby the series, will converge. And what you get is that the limit of that sequence, aka the value of the series itself, so the entire series would be equal to a times 1 minus 0, so just 1 on top, and then that 1 minus r stays on the bottom. So you can consider the formula that way, or you can put this a times 1 on the top and make it a over 1 minus r. I guess that's kind of the cuter version of that formula. But the key takeaway here is that this only has a limit of 0 if r was a fraction, so that higher powers of it got smaller and smaller to 0. That's how we got converge here. So the other side of this is that if the absolute value of r is greater than or equal to 1, then you don't get that limit. You get diverge because you'll get a dne here. So I guess we would just say that the geometric series diverges, and we wouldn't actually compute this sum. So this is going to be our key. So let's go back up to our 3 examples here. And we can look at all of the R values and decide whether the geometric series will be convergent or divergent. So in this first example, my R was 1/3, that's a fraction less than 1. So I know that this particular series is convergent, which means I can feasibly add up all of these numbers forever and come to some sort of finite number as the sum. It doesn't actually add to infinity. This one has an R value of -7/6. The absolute value of that is 1 1/6, right? It's 7/6. That's bigger than 1. That tells me that this geometric series will diverge. Let me circle these so they stand out a little bit. All right, and then finally, in this last one, we'll come to the R value here. R is 1/2, that's smaller than 1. So if you add these numbers forever, it really will add up to some sort of finite number, so we'll say convergent there. So that's how we're going to use these rules that we have in red down here. So if the absolute value of R is less than 1, you say converge, otherwise it'll be diverge. And if it's convergent, we actually have a formula for, essentially this is the formula for the limit of the sequence of partial sums, but you don't have to think about the partial sums, you can just jump straight to the formula, A over 1 minus R here. So let's go to the two that are convergent and actually use the formula to compute the sum. So in this one, the sum would be equal to, we're talking about the entire sum, 0 to infinity of 2 times a third to the k. It should be equal to A over 1 minus R. So my A value was 2, then I have 1 minus R, like that. And that's just me using this formula down here that I can't get on the screen at the same time on these pieces of information here. Okay, so I'll spend a couple of lines simplifying what I have here. You can throw this straight into a calculator if you want, but it's nice to get the exact value as a fraction instead of rounding a decimal. So 1 minus a third would be 2/3. 2 divided by 2/3, we'll kind of continue it down here, would be 2 times 3 over 2. I'm just multiplying by the reciprocal down there. The 2's cancel, and what I get, weirdly enough, is 3. Right? So this tells me if I add up all of these terms forever, it would land on exactly 3. That's what we mean by it. It's a finite sum. You get an actual concrete number here. All right, so this next example we said diverges. So we're not going to use that formula for the sum. This one just doesn't converge to a particular sum value, so we'll leave it there, but this one does. So we can use the formula one more time here. We'll say, okay, this sum, and we were saying equals, 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 so why don't we keep going that way? Okay, so we said it was convergent, and we've already done a lot of the work, right? We decided what the A and the R were. So I will have A over 1 minus R. Okay, and again, take a little bit of work to simplify. 1 minus 1/2 is 1/2. Divided by 1 over 2 is times 2 over 1, so this one adds up to the number 8. So if you add 4 times 1 plus 1/2 for the 4th with an 8th, blah, 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 forever, it'll add up to exactly 8. And that's how we use the rules for how if it converges, and if it does, exactly what the sum is equal to. Okay, let's do one more example. What I want to show you here is an example of a geometric series, but with a negative R value. So let's say we have 3 minus 3 over 2 plus 3 over 4 minus 3 over 8. We'll say dot, 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 continue that pattern. So let's say we're being asked kind of the same question that we were answering above. So is this convergent or divergent? So we need the A and R. And then if it's convergent, compute the exact sum. So I'm going to treat this one very similarly to this example here with the 4 plus 2 plus 1. I'm going to factor out my first number so that I can find the A and R, and those will help me answer the rest of the question. So if I factor out the 3, I get a 1 here, which is by design. And then minus, this is 3, it's going to be 3 halves divided by 3, so I get 1/2. 3 over 4 divided by 3 is a fourth, and we start to see our pattern here. Alright, so I can tell from what I have now that the A is 3, and my R is negative 1/2. Because I have a minus sign here. So I can see the odd powers of a half are giving me those minus signs, and the even powers, they give me a plus sign because the minus signs like cancel each other out because there's an even number of them. Alright, so the absolute value of negative 1/2 is smaller than 1. So we can tell that this series is convergent. So to find exactly what it adds up to, we'll use our formula for the sum here, which is a over 1 minus r. We've already done all this work to compute the a and the r. So we have 3 over 1 minus, and then my r was negative 1/2. So this is a over 1 minus r, but r was a negative number. So that negative number goes right into that spot of the formula. So in my denominator right here, I actually have 1 plus 1/2. So that's 3 over, this is 2 over 2 plus 1 over 2 is 3 over 2. That's 3 times 2/3. I'm just multiplying by the reciprocal of that denominator. Nicely, the 3's cancel, and what I get is exactly 2. So even though we're adding and then subtracting and then adding and then subtracting, it's like little tiny bits as you go, and it'll zero in on just about the number 2. So it'll be a little bit above, then a little bit below, and a little bit above, and it kind of evens out to 2. Okay, so that's the end of this video. I want to call your attention to the worksheet. There is a worksheet for series practice that's posted on Brightspace as well. This is what it looks like. So you have the nth term test just to practice, and then the rest of it, 4, 5, 6, just determine the a and the r. And then on the back you have a bunch of practice with the question that we just answered. So decide if it's convergent or divergent, and then if it's convergent, compute the sum. So all 4 of these examples will be done in these worksheet solutions, so they're really great practice before you actually jump into the bookwork.